All right, guys. So in the last video, we did chi-square tests for one-way tables. So when we have one variable of categorical data and some frequencies in there. In this one, we're going to do another chi-square test, and this time we're going to do it for when we have two-way tables, which, as you remember from back in the first unit, that means that we have a table like this where there's two different variables. This one happens to be political party and gender, and we can see how they are related here. And we are going to try to use this hypothesis test, the chi-square test, to determine if these two variables are associated in any way. So starting off, let's talk about some vocabulary here. Two variables are considered associated if they are related or dependent. Okay, so if one variable affects another, then we call them dependent or associated or related. So we can talk about how weather and what you wear outside are two associated variables. If it's cold, you're going to wear warmer clothes. If it's warm, you're going to wear cooler clothes. Those are associated variables. On the other hand, two variables that are not associated are variables that are not related, and we also call those independent variables. So it'd be easy to think of two different categorical variables that are not related in any way. We could talk about the weather again and relate that to, I don't know, your grades in school. The weather should not be related to your grades at all. So we would say those two variables are independent. Okay, so when we're computing our chi-square statistic for these two-way tables, they are calculated very similarly. The chi-square statistic, you can see down here in step 2, is the exact same as it was before. It's the observed value minus the expected value squared and then divided by the expected value for each category, and then all of them are going to be added together. So the question is, we have our observed values here in our table, but how do we get the expected values, okay? And we did talk a little bit about getting expected values in Unit 1 when you have a two-way table. So this is a little bit of review even. So here's a step-by-step process for finding the expected value. And it's basically given to you in formula form right here. The expected value is always going to be equal to the column total divided by the full sample size, and then multiplied by the row total. So the first thing that we need is we need to find those marginal values, basically. So in order to determine the expected values, we first have to assume that the variables are going to be independent. Our chi-squared test is actually going to determine the p-value being the probability that our values are differing from our expected values due only to chance. So we assume they're independent, that'll be our null hypothesis, and we try to show that that's false, okay? So we always start by assuming our null hypothesis. This time we are assuming the variables are independent as our null hypothesis, okay? Then to the math here, it says identify the marginal distributions. Identify the marginal distribution. There's a word you haven't heard in a while. So our marginal means totals. So we have our totals in this row. So this is the total number of Democrats, the total number of Republicans, and we have more marginal distributions or more totals in this column. There's 225 total males, 175 total females, and then here in the corner, you can see our sample size. The total number of people interviewed was 400, okay? So a lot of times when you get these two-way tables, you won't actually have any of this total data. Sometimes you do, sometimes you don't. So that first step there, or actually step 2 it says, is just to make sure that we identify those marginal totals, which we can get just by adding them up. 146 plus 103 is 249. 79 plus 72 is 151. And we can add the rows to get the row totals as well. and then add the marginal frequencies together to get the total sample size. Remember how those are all related? So if that's not done for you, it's as simple as addition. Okay, so once we have those marginal frequencies, we're then going to use this here formula to calculate each expected value. Okay, and we'll do that in a second. Actually, let's just do it right here. So I'm going to make a little table off to the side here, and we'll put our expected values in it. That way they're kind of organized about the same way. So you can see I have 4 categories in here. I have male Democrats, male Republicans, female Democrats, and female Republicans. I want to make sure I have enough room in here to kind of put all my work in. I want to show my work. All right. So looking at my formula, it says I'm going to take my column total. So if I'm going to do this position, this category here first. So my column total is here. It's my 249. 249. I'm going to divide that by my sample size, which is 400. And then multiply it by my row total. So the row total for this male Democrats is 225. So when I do that, I get, I kind of ran out of room a little bit here. I had enough room on my paper though. So I believe in you. You can do it. Nope. It was 140.06. Okay, so remember that is our expected value. Notice how I did not use this number 146 in here. 146 is the observed value. This 140.06 is how much we would expect to get there. Okay, so let's do male Republicans. So for male Republicans, we had column total 151 Republicans, sample size 400 again, and row total 225 total males. So that gives me an expected value of 84.94. Okay, so you can tell when we're looking at expected values, we're not looking at these numbers in here at all. Those are our observed values. We're not even using those yet. We're just looking at our totals to get these expected values. So now Democrat females, look in here. So the column total is 249, the sample size is 400 again, and the row total is 175. So we do 249 again over 400, and this time we're multiplying by 175, which gives me 108.94. Okay, and one last cell. Female Republicans, column total is 151, row total is 175. So we do 151 divided by the sample size times the row total 175, and that gives us an expected value of 66.06. Okay, so that's how we calculate our expected values using a two-way table. So for the chi-squared statistic to be valid, each expected value is going to have to be greater than 5, at least 5. So greater than or equal to 5, I should say. So this is going to be actually our condition. So remember when we're doing hypothesis tests, or also called significance tests, we always have to start by checking our conditions. And the condition, the only condition for these ones is that our expected value has to be at least 5. Okay, moving on. Now we compute our chi-squared statistic. So once again, it looks exactly the same as it did in the last section. We just calculated all of our expected values. The observed values were given to us, so we're just going to plug them in. So starting with male Democrats, we observed from the table 146 male Democrats. I calculated an expected value of 140, I'll round it to the 10th, 140.1. We're going to square that difference and then divide by the expected. And then I add the next cell. Let's see, male Republicans, we observed 79. We expected 84.9. And then we have female Democrats. We observed 103. We expected 108.9. And lastly, we have female Republicans. We observed 72. We expect 66.1. And so that's what our chi-square statistics is going to look like, all expanded out. And then we just follow our order of operations, parentheses, then exponents, which means squaring. And then you would divide, and then you would add. And by doing that, I got 1.53. As my chi-square statistic. Okay, so that's how we compute a chi-square statistic. Next thing here, of course, as we talked about in the last section, chi-square distributions are different for each number of degrees of freedom. The degrees of freedom, when you have a two-way table, is always equal to R minus 1 times C minus 1, where R is the number of rows in our two-way table, and C is a number of columns in our two-way table. And be careful when you're counting the number of rows and the number of columns. These two numbers do not count the marginal frequencies. Does not count marginal rows and columns. Rows slash columns. Oh, actually, you can read that, huh? Rows slash columns, okay? So I say that because when you look at this table above here, it looks like it's 3 by 3, but we are not counting the marginal or the totals in our number of rows and columns, okay? So the total number of rows we have is 1, 2, and the total number of columns we have is also 2. Okay, we do not count the total row and the total column when we're counting the number of rows and columns. So we would say this is a 2 by 2 frequency table. We're actually going to put this in matrices later on, and I would consider this a 2 by 2 matrix. So if I wanted to calculate the DF, the degrees of freedom for this distribution, I would take my number of rows, which is 2, minus 1, times the number of columns, 2, minus 1, that's 1 times 1, which is just 1. So again, that's just using this formula right here. Okay, so we've got a couple really good, some couple of formulas on this page that we're going to use quite a bit. I can grab up my highlighter. It's always good to highlight these important formulas. We have the formula for the expected value in a two-way table. We have a formula for chi-square again, which we had seen before, but it's good to remember. And then we have a formula for DF, degrees of freedom, in a two-way table, which is different than it is in a one-way table, right? Okay, so once we have our chi-square statistic and our number of degrees of freedom, then we can calculate our p-value, or the probability that our numbers are varying from the expected values due only to chance. All right, so let's see. There are 3 different ways that we can calculate our p-value now. So the first thing is I can use my chi-square table, right? So let's look at our chi-square table. We have a chi-square value of 1.53 with degrees of freedom 1. So degrees of freedom 1 is my very top row here. So I'm only looking at this row, but remember, my other variable in this table is not the chi-square statistic, it's the actual probabilities themselves. So I'm looking for the number 1.53 in this row. It looks like it's somewhere between these two numbers, right? 1.53 is greater than 1.32, but it's less than 1.64. So it looks like it's 0.2 something, right? It's between 0.2 and 0.25. So it's 0.2 something. And if we're doing a hypothesis test here, we're likely trying to get a number that's less than 0.05 both of those numbers are more than 0.05. So obviously we would have to reject our null. We would fail to reject our null hypothesis in that type of situation. So I'd say with this table, I'd probably estimate it to be around 0.22, 0.23, 0.21. Hard to say for sure, but we can definitely give an estimate. Probably 0.2 is a good enough estimate even. I'll write that in here. So I would say estimate 0.2. From our calculator, we have a couple of options. First of all, we have our chi-square CDF option, which will give me the probability that chi-square takes on a value between any two given values, as long as we provide the degrees of freedom. So let's do that. So I'll come on here, turn that on, and I'll go to, again, my distributions menu where all my CDF, PDF, all of those fun things are. And we're going to go down to find chi-square CDF. Remember, PDF gives me the probability that chi-square takes on a single value. CDF is always for a range of values. I'm going to choose chi-square CDF. And again, when we're doing a chi-square test, chi-square can never be negative. Our null hypothesis will always be that our chi-square is 0. So our alternative hypothesis, chi-square is not 0, where it's not negative, means we're always going to be looking at greater than our test statistic. I'm always going to be looking at greater than that 1.53 I calculated for my test statistic. So I already have a huge number in my upper. The degrees of freedom this time we said was 1, so I'll change that to a 1 and hit paste. Let me write it in here. Chi-square CDF 1.53 to a huge number with degrees of freedom 1. Oops, where'd it go? And hit enter. There we go, 0.216-ish. 0.216. So we were actually really close estimating with our table. And again, 0.2, between 0.2 and 0.25 is a good enough p-value to tell that we are definitely going to reject our null. So nothing wrong with using our table here. All right, but there's an even bigger shortcut. Okay, and there are detailed instructions on how to do this on the back of this section. But I'm going to go through it here, and you can look back on that reference sheet if you need to later. So to do a chi-square test for a two-way table in your calculator, the first thing we have to do is we have to put our data into our calculator. Now, when we put our data into our calculator for a one-way table, we put that data into a list. Well, we don't have a one-way table this time. We have a two-way table. So when you have a two-way table, we're going to enter that data into a matrix. And I'm going to put it in a matrix called matrix A. Okay? There's a matrix for, I think, every letter of the alphabet in your calculator. The first one to come up, obviously, is just A. So I'm just going to use matrix A. So to show you how to do that, again, the details instructions are at the back of this section. So you can see on your calculator this little blue word matrix above this X inverse button. So we're going to start by hitting second, and then this button here to get to our matrix menu. And you can see there they are. There's my matrices, A, B, C, D, E, F, G, all the way to, I think, Z, and there might even be numbers down there. I don't know. So the first thing we're going to do is we're going to need to put our data into this matrix, which means I need to edit it. So go over to edit, choose the matrix you want to edit. And the first thing it does is it highlights this number here and it says 1 by 1 right now. So right here, it's asking for the size of the matrix. And remember how up here when I was talking about the number of rows and the number of columns, I said it had 2 rows and 2 columns. So we call that a 2 by 2 matrix. So on my calculator, I'm going to say this is a 2 by 2 matrix, 2 by 2. So watch what happens when I hit enter here. Look at the way this matrix looks right now. Now I'm going to hit enter. And now my matrix has 2 rows and it has 2 columns. So now I just put my data in exactly how it looks. That number is 146, hit enter, and it moves to the right. So I'm going to put in the 79 hit enter, and it moves down here to the bottom left. So I'll put in 103, enter, and the last number is 72, enter. And again, you can see, just like I said before, we do not put our total frequencies in our matrix, just like they're not included in our rows, okay? So your calculator is going to figure out those totals for itself. Don't worry about that. So now that I've got that data in there, I can go ahead and just exit out of this screen for now. So to exit out, the easiest way to do that, if I hit clear, it's going to clear out that last cell, and I don't want to do that. I'm going to hit second mode to get to this blue quit option. Okay, and that puts me back here. Now, let's go ahead and do our chi-square test. So I'm going to put some notes in here for you, some brief notes, so you don't have to look at the detailed notes at the back. We're going to now perform a chi-square test. Remember in the last section, we did a chi-square GOF test, and I mentioned there was also a chi-square test button that we weren't using last section. Now we're going to use it. So we're going to perform a chi-square test on matrix A, matrix that we just created. Okay, so let me show you where that's at. So that's in the same place as all of our tests. Where are all of our stat tests? Remember they were in the stat button? Over to the right. There's all of our different confidence intervals and significance tests that we make the calculator do for us. So again, there's our two different chi-squared tests. We did this one chi-squared GOF test in the last section. That's called the goodness of fit test. It works for one-way tables. We are going to do this one though, this time chi-square test is the chi-square test for independence that we are doing for a two-way table. So when I hit enter here, I can see right away it's definitely going to be a two-way test because it's like asking for a matrix. And it should default just to matrix A here and matrix B here, which is perfect because I already put my data into matrix A. If I needed to change this matrix A to something else, I would need to go back to the matrix menu, go down, and select the matrix I want to be in there. So you have to change it to a matrix B. So change that back to an A. I highlight my matrix, go second matrix, choose matrix A, enter. Now it's back to an A. Notice it does also ask for expected, and it asks for a matrix here as well. The cool thing about this is this portion here, it's not actually asking you what the expected values are. It's asking you where you would like the calculator to put your expected values. Yes, that means that the calculator is going to calculate the expected values for you, and it's going to stick it in an empty matrix so you can refer to it later. So just to show you what I mean, I'll go to my matrix menu real quick. If I go to edit and matrix B, you can see matrix B is an empty matrix right now. There's nothing in there. Sad. Now watch what happens when I do my test. So we're, option C, enter. Observed is in A, want my expected to be in B, calculate. Again, draw will give you the same information as calculate with a nice picture that we could sketch in for some extra points. And there we go. My chi-square statistic, 1.52. Exactly what we had before. My p-value up here, we said it was 0.216. Oops. There we go, 0.216. And my calculator, a little bit different, a little more accurate. And my degrees of freedom, just like we had, was 1. Look at all my information there, all at once. So not only did it calculate my p-value for me, it also calculated my chi-square statistic for me. So I didn't need to do any of this math in step 2 or in step 3. And I also calculated my DF for me. And on top of that, when I now go back to my matrix menu, clear out of that, back to my matrix menu, and go to see now there's something in my matrix 2. When I hit enter there, puts it on my screen, hit enter again. Look at that. There's the expected values. I can actually come up here and look. The exact expected values that we had calculated by hand. My calculator just did it all for me. So yeah, that chi-square test button is awesome. So one key thing to note when you're doing the chi-square test, I would just say that the expected values are stored for you. Expected values will be stored for you in matrix B. Okay. All right, so let's try a couple of these out. So on the next page, our first exercise is just calculating some expected values by hand. They say to calculate the expected value of this shaded cell. So remember, the expected value is always our column total over our sample size times our row total. All I'm going to do, the column total is 69, my sample size is 309, my row total is 96. So quick punch in the calculator, that is about 21.437. So we expect this cell to have a value at least close to 21.437. Okay, doing it again in the second one, same thing. At this time it says to use your calculator. Determine chi-square and the p-value for this table. So let's do that. So the first thing I need to know actually is what size is this table? Remember, the size is the number of rows and the number of columns, not including your total row and total column. So that's just these cells here. So looks like it's got 3 rows and 4 columns. So let's go matrix, over to edit. I'm done with this matrix, so I'm just going to edit that one again. This time it has 3 rows and 4 columns. And watch, when I put in 3 by 4 and hit enter, it automatically changes the size of my matrix, and I can double check to see that it matches the size of this matrix so that I know if I made a mistake. A lot of times people will mess up these 2 numbers here, but it's pretty easy to tell if I go back up. If I were to mix this up and go 4 by 3 by mistake, I would see right away there's an issue because I have 4 rows here, but only 3 rows there. So I wouldn't worry too much about making that mistake. 3 by 4. So let's put that data in. Let me do some magic. Okay, there's your magic. I got all those numbers into my table now. And then again, make sure you don't hit clear because that'll clear out that last cell. Instead, you hit second mode to quit. Okay, and I can clear out this main page. All right, so now to determine chi-square and our p-value and our df and our expected values all at the same time, go stat, over to tests, down to chi-square test, not chi-square GOF test. Bloop. Observed is an A again, expected can go in B, down to calculate, enter. There we go. Chi-square is 19.177972217. Our p-value is 0.0038733888, and our degrees of freedom, 6. All right, moving on. Let's do a full out significance test. Okay, so this first one, we're doing a significance test. We're trying to determine if these 2 variables are related. One variable is grade, the other is response. I forget what they're responding to. Oh, dress code. Responding to dress code. The first thing we have to do is we have to check our conditions. Okay, just like always in any significance test, you always start by checking your conditions, because if your conditions aren't met, then you can't do the test, and anything else is just a waste of time. So to check our conditions, what are our conditions? We only have one condition for a chi-square test. All of our expected values have to be greater than 5. So what are our expected values? So once again, I can find my expected values by taking my column total divided by my sample size and then times my row total, or I can do some quick calculator magic. We're going to want to calculate our test statistic and p-value down here, and we already know the easiest way to do that is with our calculator. So since we know we're going to use our calculator below, let's just start it now. I'm going to put this here matrix into my calculator and do a chi-square test because I know that that's going to give me my expected values as well as my answer at the same time. So I'll go to my matrix. Oops, second There we go. Edit. Choose option A. This matrix, let's see how big it is. It's got 1, 2, 3 rows and 1, 2, 3 columns. It is a 3 by 3 matrix. 3 by 3. And my first number is 80, and then 10, and then 10. Make sure you try these on your own as well. Okay, that didn't take too long. Second mode to quit. Then I go stat, over to tests, down to mine is option C, yours might be different. I don't need to change anything there. Calculate. There's my chi-square, my test statistic, and my p-value. Let me just double check that that's exactly what I had before. Yes, it is. And now when I go to look at my expected values in my matrix, it's going to clear this out. So I'm just going to go ahead and work ahead a little bit here. I'm going to put that data in here real quick while I have it handy. No, this is not the order that we normally do things in, but we're going to need it eventually, right? So we might as well write it down. So chi-square was 101.13. And our p-value, the probability, was in scientific notation, it was like 5.64 yada, 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 e negative 21. That scientific notation 10 to the negative 21 power. And remember, with scientific notation, this means that I'm going to take this decimal here, I'm going to move it 21 spaces to the left. So it's 0.0000020 zeros and then a 5. 0.0000020 zeros and then a 5. What would we round that to? 0. It's basically 0, right? You round that down, it's 0. Okay, and then the other thing my calculator gives me, my DF is 4. I like to state my DF in my when I'm stating the type of test that I'm going to do, because it tells the reader which type of chi-square distribution that we're looking at. Remember, there's a different one for each DF. Okay, so now that I have that information written down for future use, let's go ahead and go back to step 1. What were our expected values? Remember I said when we do a chi-square test, stores your expected values in matrix B. So I'm going to go second matrix menu, option 2. There's my matrix B. I can see it's in there. Hit enter again. There are all of my expected values. So I'm going to write all those down. I can see easily they're all greater than 5, so we have met our condition. So just real quick, write that in. My expected values were 52.5, 105, 52.5 here. This column was 22.5, 45, and 22.5. And you can see it's real important in these matrices to make sure your numbers are spaced well enough that they don't kind of blend into each other. But yes, I can see they're all greater than 5, or all at least 5. They can be equal to 5. They just need to be at least 5. So perfect. We've met our conditions. We can go ahead with our test. So we state our hypotheses. The hypotheses for these types of tests are the same for every single situation. Either a chi-squared is 0, which means that our variables are independent. Variables are grade and preference. And dress code preference. I can be more specific, huh? And dress code preference are independent. Okay, our null hypothesis is always going to be our two variables are independent. So name your two variables and say they are independent, which also we could say would mean that they are not associated. Remember, same thing. Not associated means not independent, or sorry, are independent means not associated. Not associated means independent. Same thing. So you can say it either way. And an alternative hypothesis would be the opposite. It'd be that the variables are not independent. which would also mean that they are associated. And remember, with any significance test, we are attempting to reject our null hypothesis so that we can support our alternative hypothesis. Okay, we want to show that there is an association between these two variables. And we're going to do that by rejecting our null. All right, so let's state the type of test we're going to do and the significance level. So I would say we will perform a chi-square test, not chi-square GOF test. This time it's just called a chi-square test for independence. With significance level alpha equals, and I don't know if they tell you in the problem, but I know in the video they say to use 0.05, just like we normally do for our significance. All right, and then we would perform our test, right? Bam, already done. We performed our test. The test statistic is 101.13. The associated p-value is about 0. So we can go straight to conclusion. What does this tell us? Well, our p-value, 0, is definitely less than our significance level, alpha, 0.05. So we can, in fact, reject our null hypothesis, which supports our alternative hypothesis. Yes, these variables are associated. So let's say that. So since our p-value, 0, is less than alpha, 0.05, we reject H naught. Okay, now so that's what we say every time that P is less than alpha, right? Now we have to say it in context. In context, what does that mean? Well, it's always going to mean the same thing in these tests. It's going to mean that they are associated. The grade level and dress code preference are associated. Ta-da, all done. Okay, let's do one more of these. Same situation. Okay, first thing I need to do is check my conditions. To check my conditions, I need my expected values. Easiest way to get my expected values is with my chi-square test in my calculator. And since I'm gonna have to do that in the future anyways, we're gonna do it the easy way. So I'm gonna put this thing into my calculator. First thing I need to figure out is how big is my matrix? How many rows and columns are there? Look at this one. There is no total row or total column this time. So I have exactly 4 rows, excellent, average, fair, and yuck. And I have 2 columns. So this is a 4 by 2 matrix. 4 by 2 matrix. So I'll go ahead and stick that in here. And turn it on. Matrix. Over to edit. 4 by 2. My first cell is 10. Bam, there it is. And now to get out of here, since it's all in there, I don't need to hit save or anything. It's not a computer. Just hit second mode to quit. I can clear off my main screen if that bugs you. I know it does me. And then let's go straight to my test. Stat, over to tests. Find the chi-squared test, not chi-square GOF test. That was the last section. Oop. Observed as an A again. Expected can go in B again. That's fine, so we're done with what's in there. Calculate. There's that information before it goes away. Let's write it down in step 4. All right. So that's for future use. Writing that down while it's handy. Let's go back up to part 1, checking our conditions. Now that we've done a chi-square test in our calculator, we can see our expected values by just going to matrix P. There they are. I'm going to just scroll over to see them. I'm just going to round them to the nearest tenth though. So that is in my first column 8.2, 13.9, 9.2, 6.7. Should have wrote expected values somewhere. I know what these numbers mean, huh? I'll label what I got. These are expected values. And my second column for Pleasant Valley is 7.8, 13.1, 8.8, and 6.3. So these are all greater than 5, which means we're good to go. Next step, state your hypothesis. H naught is they are independent. Location and customer satisfaction are independent, meaning they are not associated. And our alternative hypothesis is that they are associated. The variables are associated. Then we state the type of test and significance level we're going to use. Literally the exact same thing we wrote in step 3 for the last one. We will perform a chi-square test for independence with alpha at 0.05 again. Then we need to compute our test statistic and our p-value. Oh, guess what? They're already there. So we can go straight to stating our conclusion. Our p-value, 0.4, is definitely not less than 0.05. So we fail to reject our null since our p-value is not less than alpha. We fail to reject H naught. Remember, that does not mean that we accept H naught. We never accept H naught. It just means we do not have enough evidence to support HA. We do not have enough evidence to say there is an association. And that is it. The next few pages here are just detailed instructions on how to use your calculator. So let me know if you have more questions.